Hello YouTube, this is my fourth video in my module on binomial probability distributions, and in this video we're going to focus on finding the mean, variance, and standard deviation of a variable that has a binomial distribution. So these would be variables that could either be classified as either successes or failures. So maybe our variable is the number of heads I get when I flip a coin, or the number of even numbers I get when I roll a die, or then the number of correct answers I get if I guess on a multiple choice exam, either correct or incorrect, okay? But the nice thing about binomial distributions is that the mean, variance, and standard deviation are extremely easy to find. And as a matter of fact, we're just going to go ahead and make our first stop, this little table right here, and define them. So we say the mean. How would you find the mean of a binomial probability distribution? Not just any, discrete probability distribution. Well, what we would do is we take n times p, and recall that n is representing the number of trials. We could also refer to this as our sample size. Remember, we have to have a finite sample for something binomial, times p, where p represents the probability of success. Probability of a success, whatever we define a success to be. In terms of variance and standard deviation, you'll notice that we say sigma squared, which is our population. Variance here is the same thing. It's n times p, but times q, where q represents the probability of failure. So probability of failure. Essentially, we could calculate all of these measures just by knowing the number of trials, the probability of success, and the probability of failure. So we say mu, which is our mean, is the number of trials times the probability of success. Sigma squared, which is our variance, is n times p, what we just found, times the probability now of failure. And recall that the standard deviation is always the square root of the variance. Maybe we should write this again. We say variance, the square root of this, is equal to the standard deviation. So that being said, let's just go ahead and put this into practice. To show you how easy it is to work here. We say, excuse me, a coin is tossed 4 times. So this would be the size of our sample, or the number of trials we've done here. So let's find the mean, the variance, and the standard deviation of the number of heads that will be obtained. Okay. So reading this last sentence, it occurs to me that really what we should do is define, first of all, the success in this experiment as being heads. Get a heads. Okay. So failure, since that's not what we're concerned with here, is getting tails. We'll call that the failure. Okay, so having defined success and failure, let's write down what we know. We say n is equal to 4. What is the probability that I actually get a heads in this experiment? We know that this is 50%. We could say 0.50 or a half. We say q. Q is the other probability here that adds up with our probability of success to be 1. So we say the other 50%. But now that I know these things here, let's go ahead and find the average number of heads I would expect to get. And think about this. Honestly, if you flipped a coin 4 times, it's a 50% chance you get heads. I would expect maybe like two heads, thinking about this. But actually working this out, we say, well, then mu is equal to n times p, n is p, where we had 4 trials. We have a 50% chance of success, 0.50. So if we were to multiply these together, hey, you get 2. Actually, we should label this 2 heads. But honestly, that's reasonable. So if we wanted to find now the variance and standard deviation, let's start with variance. It'd be 4 times the probability, which is our n, times probability of success, which is 0.50, times the probability of failure, which is the other 0.50, q, and we would end up with this, just 1. Okay, so now we say not 1 heads, because it'd be a heads squared, which is a weird thing about variance, but we get 1 as our variance. But we say now the standard deviation would be the square root of our variance. Well, the square root of 1 is just 1. So we'd say this is 1 head. So essentially, what I can tell you is this. On average, if you flipped a coin 4 times, you'd expect to get probably like 2 heads, probably, give or take 1 head, which is the spread of our data set here. And one thing I want to recognize here is this. If we had actually taken the time to fill out a probability distribution here, that is, go x and then p of x, and do this like the old school way with average, we say we get 0 heads, 1 head, 2 heads, 3 heads, or 4 heads, and actually fill out the likelihood of these things actually occurring. And I believe it's out of 16, all of these. I don't really want to do this. But if we had actually done this and then gone through and calculated the average, you would have gotten the same thing you did as when you took n times p. So I don't know, with me, I'd say, man, I'd rather do this any day of the week to find the average, the variance, and standard deviation. So let's go ahead and put this into practice down here. What if we had a really large sample size? That is, if we rolled a die like 480 times. We say this is our n. I want to find the mean, variance, and standard deviation of the number of twos that will be rolled. So this one's a little bit interesting here. We say success. Well, what is a success? Since I care about 2's here, this will be roll a 2. We want to define this right off the bat. So what is a failure? I'm just going to call this not 2, the complement to getting a 2. So that being said, let's write down the things that we need here. We need, first of all, n, which is rolling a die 480 times. We say, well, what's the probability I get a success? Well, in other words, how likely is it that I actually roll a 2? That's what we defined as being success here. This is actually a 1 in 6. We say probability of failure then would be the other 5 out of 6. And of course, we could dig out decimals for this, but I'm just going to leave them intact for the moment here. We say, well, then our average, our mu, would be n, which is 480, times our p, which is 1 out of 6. And a 6 to 480, let's see, 6 times what would be 48 here? Well, 6 times 8 would be 48. So we say this would be 80. And I want us to think about this, 80 2's. I'll write it in quotations there. We would get 80 2's when you roll this. But think about this. Of the 480 here, a sixth of them would be 2's, theoretically. So I would expect on average to get about 80 2's. So we say, well, what is our variance to standard deviation then? Well, we say, well, sigma squared. In this instance, instead of writing 480 times 1 6 times 5 6, I'm actually going to take the number we just got here. I'm going to recycle it. Because I already know that I'm taking n times p. Let's now take this times q, which is 5 out of 6. Okay, so 5 out of 6, if you were to multiply straight across here, I suppose we get 400 sixths, and we could throw this into a calculator. 400, we'll drag this down here, see a little bit more easily. 400 divided by 6. So we're going to get a decimal value here, but we say the variance here is about 66.66 or 66 and 2/3. This is our variance. And to find the standard deviation, of course, it'd be the square root of 66.6 repeating. We can just pull this calculator back out and say, well, all right, well, I'll hit the square root key. So about 8.16-ish. So about 8.16-ish 2's. Okay, so basically on average, if you rolled a die 480 times, you'd expect to get about 80 2's. Give or take about 8.16 2's in terms of the standard deviation. Okay. Now, last but not least, let's do a little bit more practical application here. If we were actually collect data on things, so like if we're a life insurance company, this one says the stat bulletin published by Metropolitan Life Insurance Company reported that 2% of all American births result in twins. Okay. So it says if a random sample of 8,000 births is taken, find the mean, variance, and standard deviation of the number of births that would result in twins. So starting with what we know, we say, all right, success. Success, in this case, we care about twins. So we say twins. So failure, not that that's a bad thing, but we say not twins, or twins bar, if you want to represent it using proper notation. Twins with a bar over the top. But basically, we know this. We say, well, our sample size is 8,000 births. We say the probability of actually getting twins is 2% of the time, so 0.02. So failure is getting anything but twins would be the other 98% of the time. But knowing what we know, we say, well, then the average number of twins we would expect to see in 8,000 births would be 8,000 times 0.02. Think about this. You're really just finding 2% of 8,000. So we'd say, well, 8,000 times 0.02. So it's 160. So you'd expect to see, on average, about 160 sets of twins. We should label that. We say, well, what's our variance then? What's our sigma squared? Well, this would be the number we just got, this 160 here. We'll recycle it, 160 times now the failure rate, which is 0.98. And so we'll take the number we just got here, this value, this 160 times 0.98, 98% of that is 156.8. So about 156.8, and that's an exact calculation. So now we are going to use the variance to find the standard deviation. So the square root of 156.8, getting our calculator back out here, 156.8, square root of this is 12.52. So about 12.52 twins. So in other words, if you were to have 8,000 births at your hospital, according to the data that you've collected so far, you'd expect to see about 160 sets of twins, give or take about 12.5 sets of twins. Okay? So that's how you would use these formulas to calculate mean, variance, and standard deviation. Very easy to do with binomial probability distributions. Cheers.